then the question is, how long do you expect to stay in state 0? Now the time spent in state 0, let us call that a random variable. So we are talking about the random variable which represents the time spent in state 0. So its density function is given by lambda e raised to minus lambda t. Where now, notice that t is between 0 to infinity. It would not make sense if t is negative. So this starts at t equal to 0. And here's an example. Now we are going to come back to these when we will look at reliability, and we will see how these distributions arise naturally. So we will try to model some process, and we will find that by making some appropriate approximations, we do some calculation, and we will come up with these distributions. So in some situations, lambda is the exit or failure rate. The rate by which you exit some good state. So then the probability of an exit during t and t plus dt is given by e raised to minus lambda t multiplied by lambda dt. So here we see that we see the density function. So basically we are at, so time t spent in good state has an exponential distribution. Now this is also referred to as the sojourn time. So remember we were talking about a particular problem, and I was talking with Angel Joe about a particular problem, and we were wondering about a certain transition from one state to another state, and we were wondering if it can be modeled as exponential distribution or not. But this is a rather common assumption. And it is very nice if you can model your process by using exponential distribution for the time spent in a state, because that makes your analysis much easier. Now let me mention that there is a generalization of exponential distribution which is called a Weber distribution. Now notice the exponential distribution has only a single parameter. There is a distribution called Weber distribution, which is very popular among researchers on reliability, even though we will not use it that much. So sometimes you try to fit something and exponential distribution doesn't fit quite nicely. You can go to Weber distribution, and it has two parameters. And because it has two parameters, then it fits, you can make it fit better. And a special case of Weber distribution is exponential distribution. So Weber distribution is more general. So if you want to make something fit not better, you can use Weber distribution. Although in our work, we will mostly be using exponential distribution because it makes the calculations more tractable. And in this class, I guess our basic objective is to see the basic ideas. But when you want more accuracy, more exact modeling, you can go back and find out how you can come up with a more refined, more detailed calculation. Okay, now let's talk about variance and covariance. Now we were talking about variance a little bit, right, when we were talking about sigma. So it is a measure of spread. So that the homework assignment, we will call it feedback module 1, will be available on REMCT, so about sometime around 6 o'clock today. And there's a quiz that is already available. So one of you have taken it already. So go ahead and take that quiz. And I think you have to allow for some time. Let me see. So you already took the quiz, right? So how long did it take?
It took about an hour.
About an hour. So you allow enough time. Even though it is called a quiz, it actually will require you to go back, look up things, and maybe even do something on a piece of paper. So allow enough time. And you can take it twice. So, and it is available until
25th.
yeah, until Saturday, yeah. Okay, so let's look at variance. So it is a measure of spread, as you know, and here's the definition. Variance for a random variable is given as the expected value of random variable minus its mean squared. Sometimes you put a subscript for mean. Sometimes you want to explicitly say this is we are talking about mean for this random variable. In that case, sometimes people will put a subscript. And standard deviation, that is actually equal to variance square root. Okay, and what is sigma? Sigma is standard deviation, usually for a normal distribution. Thus, if your distribution is not normal, you should probably not use symbol sigma, although probably people do. Covariance, let's look at covariance. Now sometimes you have two things that have some kind of relationship between them. And so that means you have two random variables which are not totally statistically independent. In that case, you want to be able to measure the statistical dependence using covariance. So this is a measure of statistical dependence. And it is given in this way. Covariance of two random variables, x and y, is given by the expected value of this product, and this product happens to be x minus mu and mu x, y minus mu y. Now here you see that we needed to put a subscript there. So mean of x, mean of y. And sometimes it is normalized. And then we call it a correlation coefficient. And that is given as rho x and y. and that is given by the covariance between x and y divided by sigma x, sigma y. Now this correlation coefficient is between 1 and 0. If you take the absolute value, it is possible for two things to be negatively correlated. Something goes up, other thing goes down. And, or they could be positively correlated. And so if correlation coefficient is 1, that means two things are exactly correlated. And if correlation coefficient is 0, that means there is no correlation whatsoever. And this is a useful measure. Sometimes you want to consider, most of the time we will make the assumption that the failures are statistically independent, but actually in many cases it is not true. And if you want to do a more accurate analysis, you should take statistical dependence into account. And if there is time, I will mention about some work we did a while ago where we came up with some ways of taking into account this statistical dependence in the failure processes. And let me give you an example. Okay, how many of you are interested in getting rich? Okay, you're not interested in getting rich? Okay. Okay, so again, even if you're not interested in getting rich, you might find it interesting. You know, there are in the stock market, there's a thing that you can invest in, and it is called an ETF, which is a you can buy and sell the shares of it. And they have invented some ETFs that are negatively correlated with some component of the market. So for example, if you are hoping that the market is going to go down, if you're expecting, then you can buy one of these inverse ETFs. So if the market goes down, your ETF will go up. And in fact, they try to make sure that it's strongly correlated for a single day. So if the market goes down by, so the market goes down by 1.5%, your ETF will go up by approximately 1.5%. And there are even more aggressive ones. So there are some doubled ones. So if market goes down by 1.5%, your ETF will go up by 3%. But unfortunately, they can manage this correlation, strong correlation for about a day or so. So for a long period of time, this correlation doesn't hold quite that well. So I thought I'll mention that. But people haven't figured out a good strategy for exploiting these. And the reason is that people haven't figured out a good way for predicting the stock market. How many of you would like to predict the stock market? So, well, if you find out a good way, let me know. So, so we can all be rich. I have thought about this a little bit, and I have probably some ideas, but I guess they need to be validated. Okay, so okay, now let us come to stochastic processes. So far, we have been talking about variables, random variables, and now let us talk about random processes. A stochastic process is basically something that takes random values at different times. And